picking up from where we left off. This is the 5th video in the 1D kinematics. It's going to be finishing up the graphs, although we might save just the practice problem slide, which has multiple questions, for its own video, just to save on space and time. This slide is got a lot of great information, so please take the time, pause if I'm going too fast, and read it all on your own. But you have the three graphs, xt, vt, at, which we'll still get to here in a moment. To go down a graph, x is always the first graph, v is the second graph, a is the third graph. To go down a graph, you're going to do calculus, which is called a derivative. For those of you not in calculus class, you know it as slope. If you take the slope between any 2 points, you will get the value for the next graph down. So if I give you an xt position graph, if you choose 2 points and calculate the slope between those 2 points on the line, you have just calculated the average velocity between those 2 points, the value on the graph below it. If I gave you a velocity versus time graph, and I asked you to calculate the slope of the graph, you just calculated the average acceleration. And I will emphasize average. Calculating the slope will always give you the average between the 2 points and time on the graph that you chose. If you want instantaneous, that's where you have to do a tangent line. And then you still calculate the slope. Being able to calculate slope of your lines is a crucial skill because it will allow you to do simple algebra 1 skills and not have to do the physics algebra equations. It will always work, and it will always be quicker, faster, and more efficient. And when you're taking a test or a quiz, you want efficiency. So we'll take a look at the graphs, all three of these, and how they link together. So here, if you remember during the first 4 seconds, we had an exponential increase in the line. That means the object was moving in a positive direction, and therefore it would have a positive velocity with a positive acceleration. And you can see the velocity is increasing over time, and then it's got a positive acceleration. I'll give you a second just to read through these and link them, and then I'm hopefully not going to go over your head as I try to show you a neat trick, an alternative way of doing these graphs purely based on slope techniques. There are 2 questions you always want to ask yourself. Is the slope positive, negative, or 0? That's the first question. The second question is the positive, negative, or 0 slope that I've already identified, is it constant or is it changing? So here we go. I'm going to choose this point and this point between 0 and 4. I know that it's not a constant slope. It's not a straight line. It's exponential. But I'm just connecting this point at 0 to this point at 4 seconds. In other words, if I drew a line so that it looked like this, is that line positive, negative, or 0 slope? And hopefully you're saying that's a positive slope. That means down here, I'm going to be in the positive quadrant. If I go back and I use my slope here at the beginning, it was no slope, then it's more positive, more positive, more positive, more positive. It's basically trying to exponentially get to a vertical line, which means at which point in time the slope would be infinite. It'd be so high that it's a vertical line. So I'm starting at nothing, and the slope is getting steeper and steeper. That means my positive number is getting higher and higher and higher and higher. So try it again. Connecting the dots between 0 and 4 seconds on this graph. Ask yourself question number 1, is it positive, negative, or 0 slope? The answer is positive slope, so I'm in the positive quadrant. Is the slope of this line changing or constant? It's constant. So therefore, I'm going to choose a constant line that is the slope of this line. In other words, the slope of this line is positive 4, and it never changes. That means that this line will be positive 4, and it never changes. So we'll try a different color. We'll try this again, in case I've lost you. If you need to, rewind it and try watching it again. I'm going to go from here 4 seconds. I'm going to go here to 7 seconds. From here to here, I have a positive slope. Therefore, I'm in the positive quadrant. If I physically and literally calculate this numerical value, it's going to turn out to be, looks like 15. This line never changed its slope. It wasn't exponential, which means it's going to be a positive 15, and it stays 15 that whole time. Now I'm looking at this line. Does it have positive, negative, or 0 slope? It has no slope. Therefore, I go down to 0. Does the slope on this horizontal line from 4 to 7 ever change? The answer is no, which means I'm not going to change my numerical value of 0. I'm going to maintain that 0 for those 3 seconds. All right, now here comes the hard one. Here, I've got a positive slope, but here I have a less positive slope. Here, even less positive. Here, at 15 seconds, I have a tangent line that has no slope. Then it's a negative slope, more negative slope, more negative slope, more negative slope. Which means I'm going to start at a positive number that's going to decrease, decrease, get to 0 when it got to 0 slope here, and then it became negative, more negative, more negative. This line has a negative slope that never changes. Calculate the slope of this line, it's that negative number that never changes. If that doesn't make sense, try watching it again. That's just an alternative. You don't have to memorize that. You technically don't even have to do that. It's just a quick way for you to check your own work. So we'll try one. Number 1, determining the average acceleration between 1 and 4 seconds. So, between 1 and 4 seconds. So I'm going to go from here to here, between 1 and 4 seconds. My job is to find the acceleration, not the velocity, not the position, but the acceleration. And the acceleration is one graph below the velocity graph. That means I need to take the slope. I need to take the derivative. So I need to calculate the slope of that blue line that I just added. The slope goes up 20 over 1, up 20 over 1. So the average acceleration between 1 and 4 seconds would be the change in velocity over the change in time, if you want to use the physics. Using the slope technique, I've already figured out that it's 20 meters per second every single second. But I can plug in the numbers to check. I'm physically calculating the slope. 100 minus 40 divided by 4 minus 1. That's 60 over 3, or 20. And that's where being able to do the slope is always going to be quicker and more efficient than using the physics equations, because I'm using the average acceleration equation. And I'm going to get rid of that blue line. Now my job is to find the instantaneous acceleration at 1 second. Remember, instantaneous means tangent line. So I'm going to draw a tangent line that only touches the graph at the 1 second. And because you're drawing this by hand, individual students could have different results, but we're looking for technique, not the absolute best correct answer. But again, for this one, I would be calculating the slope. So what I would do is I would go from 40, I would go up to 80, so I go up 40, and I go over 1.5. So up 40 divided by 1.5. Or I could do the physics, again, same equation. I'm using the acceleration equation. I'm taking the 80 and the 40, and I'm taking the 2.5 and the 1. It would be 40 divided by 1.5 or 26.6 repeated, which means I would probably just chalk it up as 27 meters per second per second. Okay, now comes the new part. How do you find the displacement? Displacement is going to be the graph above this. So calculus people, what's the opposite of a derivative? Hopefully you're going to say integral or antiderivative. For anyone not in calculus, the opposite of your slope is your area. So between 4 and 9 seconds is this shaded region. It makes a perfect triangle. Calculate the area, and that will take you up a graph. And again, just like doing slope to go down, doing area to go up a graph is much more efficient and quicker. Because for this, I just calculate the area of a triangle, and it's 1/2 base times height. 100 is the y-axis, that's meters per second. Height, or base, got that backwards, sorry. Base is going to be the seconds, height will be the velocity. What is a meter per second times a second? And you get a meter, so you even get the right unit. It means you travel 250 meters. If you didn't do this, you would have to do physics equations, which we'll do in a practice problem here in a little bit. Again, the problems don't get any easier or harder, they're just different. It's the same skills, just different graphs with different numbers. So you want to practice as many as you can, as often as you can. So I will come back to this in the next video, because this is 9 practice problems with each of the 3 graphs.